George didn't go to school, um, except for I think like 1 year. The essay was 70 pages, and I think he published it himself. He didn't think that he deserved to be published in a math journal because he didn't have any education. The statement is about calculating flux and flow by using the divergence and curl. A vector has two components, magnitude and direction. So when you ask, how is a vector field changing, you could be asking, how is its magnitude changing, or how is its direction changing? If we want to measure how is the magnitude of a vector field changing, we call that the divergence. And if we want to measure how the direction of a vector field is changing, we call that the curl. A water table is a child's toy. You hook a hose up to the bottom of it, and water pumps into the little table, and then, kids just enjoy splashing around in the water, and usually the water spills over the sides of the table. So let's suppose that water was being pumped into the table at a rate of 5 liters per minute, and water was draining out of the table at a rate of 2 liters per minute. Obviously, there's more water being added to the table than there is being taken off of the table. So eventually the table will fill up and water will start to flux across the boundary of the table. It's pretty obvious in this case that the rate at which water would flux across the boundary of the table is 3 liters per minute. This would be true even if we weren't limited to just the instance where there was one pump and one drain. Suppose that the region was partitioned up into a bunch of little pieces. Each of them was dA, and then in each one of those little rectangles, there was either a pump or a drain. Sometimes we call these pumps sources of water, and the drains, we call them sinks. Just like when there was a single pump or a single drain, you could calculate the total rate at which water was passing across the boundary by adding up all of the pumps and drains for each point inside the region. I want to point out that this conclusion is a relationship between objects that are going on inside the region and a rate at which something is happening on the boundary of the region. So this is Green's theorem. I think that when you view it in this simple form, it seems really obviously true. So now imagine a paddle wheel, but we're not going to orient it in the same way that you would imagine a paddle wheel oriented like on one of those old school steamboats. So we're not orienting the paddle this way. It's not oriented so that it would like propel a boat forwards. It's oriented straight up and down so that if you put it in the water and you spun it around, it would kind of make like a little whirlpool in the water. So this concept really only makes sense in the instance that we imagine that it takes no work to move the water. So the water doesn't count. All we're saying is if I dropped a little boat on the boundary of this water table, however much work it would take to push the boat around the boundary of the water is the same amount of work that it would take to spin the paddle wheel. So suppose that some of the paddle wheels were spinning in the counterclockwise direction, which is the same way that the boat is going, and some of the paddle wheels might be working against the movement of the boat, so maybe they're rotating in the clockwise direction. You could add up all of the counterclockwise spinning paddle wheels, the work that they were doing, and then subtract off all the clockwise spinning paddle wheels, and what you would get is the total work to push a little boat around the boundary of the region. Again, this is a relationship between what's going on inside the region and what's going on the boundary of the region. Let's just remind ourselves briefly what this object del represents. So del is an operation that's like taking the derivative, and the derivative should be some kind of measure of change, and what we do is we imagine taking a small step in a direction and measuring the change in the output. The way this object worked in Calc 1 was you imagine taking a small step from x1 to x2, and then the derivative is the proportional change in output. So we're trying to figure out how much torque there is at a single point inside the region. This is rotational force, and I'm going to try to convince you that we can calculate the curl by doing del cross F. Recall that there's a relationship between the magnitude of the cross product of vectors and the sine of the angle between them. So cross products are large for perpendicular vectors, and cross products are 0 for parallel vectors. I'm going to use red to represent the taking a step. So back in Calc 1, that was this little distance between x1 and x2. And then I'm going to use blue arrows to represent the force. Remember that I'm trying to calculate the change in F, but just to make that more simple, I'm going to assume that F of 0 is 0. So let's suppose that I took a small step, and this time it's just straight down the x-axis. What I'm trying to do is to produce the picture where del cross F is as large as possible. And remember, del cross F is going to be as large as possible when the angle between the step that you took and the direction of F is perpendicular. So that means that F must point in this direction in order for del cross F to be as large as possible. Okay, now let's imagine that we took a step in this direction. Then just like before, I'm trying to draw a vector that makes the cross product as large as possible, so I need to draw a vector in the perpendicular direction. Okay, one more here. I think you're starting to get the idea now. If I took a step straight up the y-axis in the vertical direction, then again I'm going to have to make a 90-degree angle in order to make F be as large as possible. So if I continue this process in all the possible directions that I can take, I produce this familiar spin field. So this means that del cross F is doing the job that we want the curl to do, because when you have a field that represents a paddle wheel spinning, del cross F gives this a large positive value. So what we're going to have to do is figure out how to turn this vector into a scalar. We're going to have to just pull out the amount of force that we want. Whatever del cross F is doing, because of the decisions that we made about the right-hand rule, it should give a positive value to vector fields that are curling in the counterclockwise direction and a negative value to vector fields that are curling in the clockwise direction. Okay, now I'm going to try to convince you that del dot F should be a measurement of how much the vector field is being produced or lost at a point. Okay, so the behavior of del dot F depends on the cosine of the angle between the vectors, and cosine is largest when the vectors are parallel. All right, so I'm trying to draw a picture where del dot F is large, and this should be an even more trivial picture to draw, because if I take a step down along the x-axis and now I want to draw a vector that's parallel to that, then I just need to draw another vector that's down the x-axis. Okay, so this is the picture that you get if you try to draw a field where del dot F is large. And this is also the picture that you should draw in a scenario where water is being pumped onto the table. So this means that del dot F is doing the job that we want to do when we're measuring the divergence. Okay, and just for the sake of completeness, the vector field where all the vectors are pointing at the origin is the vector field that should have a negative divergence. So another easy way to think about what the divergence and curl are measuring is the divergence of F is measuring how much F looks like a field where all the arrows are pointing away from the origin, and the curl is a measurement of how much the field looks like the pure spin field. Okay, so here it is. We've got it now, Green's theorem. So we're going to imagine a region, and we're going to call the boundary of the region C. So that's going to be some kind of parameterized curve. Oftentimes you will see in math textbooks the boundary of a region also written del R. The idea of del is that it's supposed to just be a small change, and if you took a region and you made it just like a little bit bigger, then the amount that it is changed by is just like a thin strip that goes around the boundary of the region. So that's the logic behind calling the boundary of a region del R. But anyways, we're going to call it C, and then you have to make necessary assumptions about partial derivatives existing, and then we get these beautiful relationships. I just want to point out that from the point of view of making math problems easier, this absolutely does that job. On the left-hand side of the theorem is a line integral, boo, right? I mean, you got to parameterize the curve, you got to calculate all these differentials, you got to plug everything in. On the right-hand side of the equation is a double integral, and that's really easy. You just got to use the laser beam method, and then you just use Fabini's theorem. Okay, so I just need to talk about this dot K at the end of the tangential form. Remember that torque is a vector that points in the direction of the axis of rotation. So since this problem is imagining the fluid flow being constrained to the xy plane, that means that the paddle wheels that would be spinning in this fluid flow are pointing in the direction of the z-axis. So in this problem, the axis of rotation is in the direction 0, 0, 1. Okay, this guy's skeptical, and I don't blame him. I'm just going to try to argue that this is true by adding up the divergence everywhere inside the region. So I've drawn two little blocks inside the water table. So that's like maybe two little adjacent pieces. I've drawn these two red arrows. Let's suppose that they're the direction that the vector is pointing in. The outward normal vector in dA1 is pointing in exactly the opposite direction of the outward normal vector in dA2. So what that means is that when you project the force field onto N1, you'll get exactly the opposite thing as when you project the force field onto N2. Okay, so what that means is when you're adding up the divergence on the interior of the region, the divergence that's going out this way from dA1 right here will cancel with the divergence that's going out this way from dA2. But look, there's also that, then there's like another little dA3 down here on the bottom. So whatever the divergence coming out of the bottom of dA1 is, that will cancel with the divergence that's coming out of the top of dA3. So that means that any time that one of these little area differentials is adjacent to another area differential, all of the divergences on those boundaries are going to cancel. I can see some rectangles, though, that do not have an adjacent area differential for their divergence to cancel with. Here's an example. Here's another one. This guy has there's no other little rectangle over here for that divergence to cancel with. All of the divergences will cancel except for the parts that are pushing out across the boundary, which is exactly what we're trying to calculate when we calculate the total flux. The normal form of Green's theorem says that the sum of the divergence everywhere on the interior of the region will always give you the same value as the flux across the boundary of the region. All right, I've convinced him about divergence, but he still doesn't believe me about curl. Now I'm going to try to add up the curl everywhere on the interior of the region. So on the right side of dA1, the unit tangent vector is pointing straight up, and on the left side of dA2, the unit tangent vector is pointing straight down. So that means that these two curls are going to cancel. The amount of curling that's happening on the right boundary of dA1 is going to cancel with the amount of curling that's happening on the left side of dA2. But then for dA1, so here's dA1, there's also another little area, another little rectangle right below for the bottom boundary, and look, that one would be going the other way too. So everywhere on the interior of the region, the curl is going to cancel out. except for the rectangles that have one of their walls along the boundary of the region. The tangential form of Green's theorem says that the sum of the curl everywhere on the interior of the region will always give you the same value as the work to move a particle around the boundary of the region. Okay, I'm changing this guy. He believes us now. Okay, so hopefully now you're convinced that Green's theorem is true, but we're still not quite there to being able to put it in a useful form because it still relies on the divergence and the curl, and we don't have simple expressions for calculating these things. Recall that del is a vector with the partial derivative operation in each of the coordinates, and then I'm going to name the components of the vector function m and n and p. Dot products are really easy to calculate, but Green's theorem is always in the plane, so the z coordinate will always be 0, so we get this simplified expression for the divergence of f in R2. Now, the curl is a vector quantity. Del cross f is doing the job of measuring the curl. So I've just set up this little cross product formula, and I'm expanding by minors this determinant. Since our fluid flow is trapped in the xy plane, then the axis of rotation always points straight up the z-axis. So the amount of curl that we're concerned with is only the curl that's happening along the axis of rotation. So what that means is we only want the k component of curl. So if you're doing a problem in R2, then this is the only piece of the curl that you care about. When we get to Stokes's theorem and we start doing some problems in 3D, then we are going to have to keep all of the pieces of curl. So this whole formula isn't useful now, but it will be useful later. Okay, that's the theory for Green's theorem. It's a really fantastic thing. It takes a phenomenon that we really believe should be true in the real world and confirms that our mathematical models are behaving as intended. And also it gives us a really easy way to calculate flux and flow. I want to point out that this does have a limitation. You can only use Green's theorem for problems about a closed region.